Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings. I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. All right, we're going to get to those equations of motion for a proton circulating around a proton accelerator. High energy physics, which has implications in astrophysics. The two are very closely related. Now, in physics, the equations of motion allow you to be able to specify where an object is in space and time, okay? The locations of the object in the X horizontal direction, the vertical, the Y direction, and the Z direction, the three-dimensional trajectory right through the page you're looking at. If you can specify those three coordinates, you know the position of an object. The x-axis, the y-axis, the z-axis, right? Horizontal, vertical, and right through what you're looking at. Now, in physics, that's not quite enough to specify where an object is. Not only do you have to know its location, but you have to know how that location is changing with respect to time, right? And that's what velocity is. It's the change in the position of an object with respect to time in a direction. Speed is the change of an object's position with respect to time. Velocity, that is the speed with respect to direction. Yes, an object's position is changing with respect to time, but in what direction? North to south, east, west, right? So that's where velocity differs from speed. Speed is a magnitude. It gives the amount of that object's change in position with respect to time. Velocity gives the direction that change is occurring in, okay? All right. So, in physics, if you know an object's position, and if you know its velocity, then you know how it's moving. You have its equation of motion, all right? And that's what we've been trying to get to for the protons circulating around the booster synchrotron at Fermilab before being inserted into the tevatron, okay? And again, the practical reason for wanting to be able to know the equations of motion for these protons is so that they don't collide up against the sides or the top or the bottom of the quadrupole magnets that they have to travel through as they're being accelerated around the booster synchrotron, okay? All right, so let's continue on and let's get to those equations of motion, shall we? Yes, let's. All right, okay. We left off right here with equating the magnetic force that the quadrupole magnets exert on the protons as they pass through the quadrupole magnets. We equated that force with the centripetal force, right? When you have an object going in a circle, there's the centripetal force. Centric, meaning center, petal, meaning seeking, centripetal, center-seeking force. So whenever, as if you were twirling a ball or a rock on a string, that force that you're having to exert to keep that object going in a circle by way of the string, that's the centripetal force that you're having to exert on that ball or on that rock to keep it going into a circle. And of course, if you were to let go of the string, remove the force, the rock or the ball would fly off, okay? So that's what we're talking about here. We have a force where the protons are circulating around the booster synchrotron, that they're not only experiencing the magnetic force because they're charged particles and because the quadrupole magnets exert a magnetic force, they're feeling that force. And in addition to that, you got the centripetal force going on, right? Gravity. Okay? So you got these two forces going on at the same time. So mathematically, we are trying to describe what's going on mathematically, okay? All right. So we left off with the centripetal force. All right. Now, let us do this. We were successful in mathematically describing the dependence of the protons as they go through the booster synchrotron. We were able to switch from their dependence in the horizontal and the vertical direction with respect to that z-axis down the quadrupole magnets. We were able to switch from that dependence on time to that dependence upon the distance down that quadrupole magnet, all right? All these equations we've looked at, that's what they were doing. They were using analytic geometry, a combination of algebra and geometry, trigonometry, calculus, differential equations, using all of those mathematical tools to physically go from describing the motion of those protons through the quadrupole magnets as being dependent upon time to now being depending upon the distance of those protons along the trajectory. So we use mathematics to switch from one reference frame to another reference frame. From time, which I've said before is cool, it's good to know, but now with respect to the distance of the protons as they travel around the proton accelerator, okay? That's what we did, all right? Okay, so let's keep going. All right. So, let's go down to these two equations right here. X and Y. Now, these express the positions of that proton in phase space, horizontally in the X direction and vertically in the Y direction, okay? And now, as you can see, you don't see any T, and that rhymes. You don't see any time dependence, okay? All you see is X. You just see X. And there's a similar expression for Y. But the important thing to realize is that now the horizontal position of that proton as it travels along the z-axis through the page, through that quadrupole magnet, now we have an equation that expresses its horizontal position with respect to S, the distance through that quadrupole magnet, okay? And the same for Y, okay? We have an equation that expresses its vertical displacement with respect to that Z, the S distance along the Z-axis. So these two equations, X and Y, and this is trigonometry, okay? We got the cosine and the sine, and we got the cosh and the sinh, okay? But what these two equations are simply saying, they are expressing the horizontal position of that proton, X, and the vertical position of that proton, Y, in phase space, right? Horizontal and vertical to its trajectory. So, S, that's its position along the Z-axis into the page. And what these two equations are telling us, that for any value of S, how far it's traveled through that quadrupole magnet, S, it tells us what its horizontal position, X, and what its vertical position, Y, is. Okay, what they are. That's what these two equations are telling us. All right? That's what they're telling us. They're relating the horizontal, the X position, and the vertical position, the Y position, in phase space of that proton with respect to its distance down its trajectory, okay? So we're narrowing it down. We're getting close to being able to get to those equations of motion, all right? Knowing the position of that proton in phase space and its velocity, okay? All right. So let's go to the next page. All righty then, let's do that.